Is this thing on now? You can hear me? Okay, so I can't see, but I don't know where she went, but it's not super important. So after my last talk, I went out of the hallway to get a drink, and this gal stopped me and said, I knew I recognized you from somewhere. You're the guy that's been yelling at us all day to get back in here after breaks. Yeah, that's me. I'm the guy yelling at people. All right, so, it was awesome this morning to see all the hands for when Jennifer's question for people who haven't been to a summit yet. I'm hoping that means that there'll be some good educational stuff in this talk. This one's really a twofold thing. It's right to provide a little bit of education. It's not going to go super deep into this stuff. It's really mainly to draw more attention to what Nate just alluded to, that virtual block devices are just a great way to innovate. They're there, the APIs are there, and we just want to call attention to it. So, without further ado, I'll exit stage right. Okay, so I can't talk about virtual block devices without doing something about the block device layer, right? That'd be pretty difficult. So I've got a couple slides on the block device layer. We'll talk about what virtual block devices are and sort of some of the common functions, how they're different than regular block devices, and we're going to talk about terminology here in just a second. Talk about some examples that maybe some of these examples you didn't realize they're implemented as virtual block devices. Maybe you did, but there are a bunch of them in the repo, so I'm going to talk about a few of those. And then we'll talk about the pass-through bdev module, sort of give you a preview of that into tomorrow's lab. So if you go to John's lab tomorrow, you're going to get to actually get in there and toy with the code, play around with the bdev pass-through module, run some experiments, and really get a feel for the power of virtual block devices. Before I actually flip to the next one, this is kind of, I don't know, I think it's kind of a funny story. As we're putting together this deck, and I sent the first draft around to mainly the core maintainers for some feedback, we discovered after 3 or 4 email chains that between us, and most of this is my fault, I'm still relatively the newcomer on the group, the terminology that we're all using was not the same. So my next slide is an attempt to define some terminology. Hopefully it all makes sense to everybody, and then I'll throw up a patch and put it on the documentation page. And if people want to comment and say, I don't quite understand this, or whatever that means, then we can change that. But the fact that 3 or 4 of us who work on SPDK a lot, we're getting confused over terminology, I just thought was a little comical. Okay, so I won't read through these, because like I said, I'm going to put them on a patch so you can see them up on the website. But I'll briefly go through a couple of really the key ones to make sure that I don't get confused or you don't get confused as I'm talking. So some of the, well, maybe I will go through each one of them. So the bdev layer is pretty obvious, right? That is the block device abstraction layer. That's all the generic code that makes it happen. And we're going to talk about some of those capabilities and functions here in a second. A bdev module, so anytime you see the word module, we're referring to the actual code implementation that creates a certain type of bdev, right? So it's right, the C code that's checked in that you look in the repo and see, oh, look, there's GPT. That's the bdev module. Bdev, without module at the end, is we're actually talking about the device, the abstracted device, the structure that you target IOs at. And there's 2 types of bdevs that we're going to define here, a base bdev and a virtual bdev. So if you hear somebody just say bdev, it's all very, very similar under the covers, same structure. It's really a matter of how you think about it and how they're used. But a base bdev, the easiest way to think about that is it's kind of at the bottom of the stack. So think about an NVMe Express. The NVMe Express base bdev talks to queue pairs, right? Whereas a virtual bdev talks to other bdevs, right? That's how we create the IO pipeline, right? Okay, so the 50,000-foot view of the block device layer itself, right? So all I've got in this picture are pictures of the modules and a list of some of the main functions. And again, if you're not new to SPDK, this isn't anything that you haven't seen before. But if you are new to SPDK, hopefully this will help you grasp the whole block device concept and the block device abstraction layer concept, because it is key to a lot of things and a lot of capabilities that SPDK provides. But you can see some of the main things that the generic bdev layer handles. The quality of service feature down at the bottom. You're actually going to hear a lot about that tomorrow. You come to Gong's talk, he'll give you all sorts of great details about how that's implemented and what it does, what the future of that looks like. Some of the other things you can see, like hot plug support, I/O statistics all come out of the bdev layer. Queuing of IOs is a bdev layer function. Handling no-mem conditions from things underneath is a generic bdev module layer function, bdev layer function. Okay, so we'll drill down a little bit to, I'll call it the 1,000-foot view. This slide took a little bit of crafting, and it's kind of a mixture of a bunch of different things, and I'll do my best to help make some sense of it. If you've tried to visualize in your head and build a mental model of all of the concepts in SPDK, and then apply them inside of the block device layer, and I'm talking about I/O devices, channels, how channels are used within the bdev layer, what's per thread, what's per bdev, and try to get all that going. It's really hard to figure out how to do this. And in fact, this is mostly Ben that helped me come up with this. But I've got a brilliant idea for next year, and all we're going to need is a lot of money, Nate. So I think we ought to get virtual reality headsets for everybody next year, and we'll do a 3D walkthrough of the bdev layer, and you can look up and look around and see where the channels are at. And you can see the bdev module, and you can see the bdev manager. You can see all this stuff and how it all ties together. I can't do that yet, but
I heard there's
but I think
certain
that's about
types
the
of
only way to do
drugs
it.
you can take, Paul, that do the same thing. Just
Okay, so let's start at the top. This is by no means an exhaustive architecture diagram of the block device abstraction layer. It's just a few of the major elements that help in understanding BDEVs and virtual BDEVs. So starting at the top, we've got the BDEV manager. And this is a structure. You can go check it out in the header files. I've listed a few of the elements in that structure in the diagram just to kind of help you as you look at this picture, get some context. All right, what does the BDEV manager do, right? A manager can do all sorts of crazy things. But you can see some of the things it's got up here. It's got pointers to data buffer pools, the bdev IO pool, all that kind of stuff is all controlled by the bdev manager. Now, the yellow channels underneath it are associated with the bdev manager, and they exist one-to-one with every thread. Okay, so you'll find one of these channels associated with bdev managers for every thread that exists in the SPDK system. Moving down to the actual bdev structure, and again, there's a gazillion elements in this structure, but some of the main ones that help you get, again, a feel for what this thing is, what it does. Off to the right, you'll see pointers to the I/O functions. We'll see some examples of that when we look at some of the code in the pass-through module, and you'll get through a lot more of that if you go to John's lab tomorrow. Other kind of obvious stuff, right? The name of the bdev, open descriptor lists, all sorts of stuff in the bdev structure itself. And then you can see there are many channels associated with as many bdevs as there are, and these again are a per thread context. So whereas there's a one-to-one between a thread and a bdev manager, there are many bdev structures, many bdev abstractions, many channels that can go with those, and each one of these channels are pointing back to the thread associated with the channel of the bdev manager that they exist on. So there's a lot of interconnectedness here, and again, there's a lot of stuff I didn't include in the picture. I tried it first, but it confused everybody, including myself. So this is the attempt at the 1,000 foot, and that's as deep as I'm going to try to go. But it's a lot easier to discuss this in Q&A than it is to put on a slide. So we've got our couple hours tomorrow and in the developer meetup section of this, and of course we've got happy hour coming up. That's a great time to pick people's brains on, wait a minute, I thought that was per module or per thread, or what's this management channel, what does that mean? And so it's a lot easier just to go through a lot of Q&A than to try and draw a 2D picture. Okay, so let's zoom back up and talk about virtual block devices. And again, they are BDEVs, same exact structure underneath, and a few different responsibilities. Or really, it's more of a how the flow is going through. And I list here, whoops. So I list here, it can intercept I/O on the way down and the way back. And that's really a conceptual thing, and I'll talk more about exactly what that looks like when we look at some of the code. But I think it's the best way to think about a virtual BDEV is I slip this thing in, IOs are coming in, it's going to intercept the IO and do something cool, pass it on down the pipeline, and on the way back up on the completion, it can do something cool again, and then pass the completion on up. Okay? In reality, you'll see in a second, it's more like IOs are actually targeted at the vBDEV, and the vBDEV creates another IO and targets it to the BDEV underneath it, but I'm jumping ahead a little bit. The other thing, Nate mentioned, this is a great place to add value, right? Because the BDEV API, especially around the BDEV, the IO function tables and the module function tables we're going to look at on the next slide, is fairly stable, fairly well defined. And the BSD license nature of SPDK, you can create a vBDEV with your own secret sauce in it, and you don't have to push it back up. And you can easily integrate it with the rest of SPDK. So this is just a great place to innovate and do things that maybe you didn't think you could do in a vBDEV. Okay, so here's those examples I mentioned, and like I said, I don't know, maybe you guys knew these were already virtual block devices, maybe you didn't. But logical volumes, if you haven't heard about logical volumes yet, you've been living under a rock. And Daniel's got a great talk on that tomorrow, so he'll talk a lot more about logical volumes and what they are, logical volume manager, and essentially the capability of taking another BDEV and carving it up dynamically into a bunch of smaller BDEVs, right, for dynamically. That's a virtual BDEV, the logical volume. We've got an error virtual BDEV that allows you to inject errors at the block device API layer. So you want to do some testing, you want to see what happens in your application if you get error XYZ at that API layer. We got a virtual BDEV to do that. GPT is another one, right? It was sort of, I don't know if you want to think about it as a predecessor to logical volumes, but I think Jim described it earlier as somewhere, it was today or yesterday. It seems like it's been a long day. But GPT does kind of the same thing as logical volumes, but it's not dynamic, right? So it's going to take GPT partitions that it finds on a base BDEV and carve them up into multiple virtual BDEVs so that you can present multiple devices to the application above you, even though they're actually all physically one device. The pass-through virtual BDEV. This one's relatively new, a couple months old. This is a great example and a template for creating new virtual BDEVs. If you go look at the code in the existing vBDEVs, it can be a little challenging to figure out what are the required function entry points, exactly what do they do? Why is this one implemented this way? Do I need to do that in mine? So this vBDEV passes IOs through, right? So its value add is, as an example, it is basically documentation in the form of C code. So we'll look at a little bit of that now, and again, you'll get a whole lot more of that if you hit the lab tomorrow. And then crypto vBDEV, Jim mentioned that earlier as well. The patch is up in Garrett Hub now. It's mostly functional. There's still some DPDK work to do, but it does work, and we do expect it to land in the next few months, and it does encryption and decryption, right? Just right in line. Supporting multiple algorithms, it can do software-based encryption, use Intel Quick Assist, again, all out of that DPDK framework. So another example of where you can slip something down a pipeline and do something cool. Okay, so sneak peek at the lab tomorrow. Again, if you go, you get to play with this code and see more snippets of it and jump in with GDB and break things and fix things and have all sorts of fun. Just a few snippets out of the vBDEV path-through module to give you an idea if you haven't looked at any of this code before, kind of what they look like. So a couple of key structures that a vBDEV module has to have, and actually a BDEV module has to have. Not all of these function entry points are required. And in this example, they're all implemented just so that you can see them, but you don't actually have to have every single one of them. This top one here, we're calling the BDEV module function table. You can see we're providing the BDEV layer with modules-related function entry points. Like, here's how I initialize my module. Call this function when you want to do that, right? When you want to have this module examine a new BDEV that's shown up in the system or a new vBDEV to see if it wants to take some action on it, you call this function, right? So it's pretty straightforward. And then we've got another function table that is much more IO focused, or more oriented towards the BDEV itself, the BDEV abstraction that's instantiated by this BDEV module. So these are, all, again, pretty self-explanatory. You've got something like submit IO, right? Well, that's the function you call, the BDEV layer calls when it wants to send an IO to a BDEV created by this module. A few more points about initialization. And again, initialization, there's a lot to it. I just picked kind of a couple of the main things. It's not a huge amount of code. You can go look at it, and you'll see more about it again in the lab tomorrow. But one of the key calls in the initialization sequence is this first one up here, the init function, which I mentioned earlier. This is called by the block device abstraction layer. It's the very first thing that happens to your module. You don't have to do something in that function if you don't want to, but a common use of that and what this module actually does with it is goes and reads the configuration file that you've set up that tells you which BDEVs you want this vBDEV module to claim and be a part of. So it reads that early on, puts it in memory, so it can use that later on in this function. And we're going to look at a lot more of this in detail on the next slide. But anytime a new vBDEV or BDEV is introduced into the system via whatever means, it could be via RPC, could be because a vBDEV has created one and registered it. Because we registered an examine callback, our module is going to get this function call with the pointer to the BDEV that just showed up. Oh, I'm going to talk a little bit more about that on the next slide. With a pointer to that BDEV, and we can decide what we want to do to it. And this is actually a couple of snippets from that examine function. So in the case of the pass-through module, right, you can see a couple of the key calls. There's 4 or 5 different APIs that we use in here, but a couple of the key ones are, if you've decided in your examine function that you want to claim this thing, you actually just make a pretty simple call to claim BDEV and say, all right, I want this guy because my configuration file told me, or I got an RPC or whatever. For some reason, I know this guy's mine. After you claim it and you fill in some structures, you do all your housekeeping, the next thing you do is do a vBDEV register. And this is where you're telling the block device abstraction layer, all right, I've got a new BDEV. It's a virtual BDEV, but again, it's the same structure. You're just saying, I've got a BDEV, see if anybody else wants to use it. And now everybody else is going to look at the BDEV that you just registered and decide if they want to claim it or if they want to do something else with it based on whatever logic they've got in their examine function. All right, and then a couple simple examples of I/O-related activities. So obviously, I/O submission is something that your BDEV is going to have to handle, and we saw that function in the BDEV module-specific function table. Again, clipped a lot of code out of this. Actually, maybe this is the very top end of the submit request function example. A couple of key things to note here, right? We get a channel, right, from whoever's calling our submit function, and we get a BDEV IO, right? Saying here's the IO that I want to send to this channel. Since this is a pass-through module, we're actually not going to do anything with the IO. I'm actually just going to, quote unquote, intercept it and pass it on. And this is where I said we don't actually, sort of pass it on. If you've played around with any of these APIs, you know that this is actually calling the top end of the block device abstraction layer and saying, I want to send an IO. And all of these parameters that I'm passing in are based on the BDEV IO that was just given to me. What this function is going to do is allocate a new BDEV IO with all of these parameters, and when it's done, it's going to call this function here that I've called PT complete IO, and it's going to give me a callback argument that we'll see on the next slide that is a pointer to the BDEV IO that I just got. And that's going to make a lot more sense on this slide. So I submit that IO, goes back in the top end of the block device abstraction layer. It gets processed by the BDEV that I targeted it at. It's going to get completed, and then the block device abstraction layer, when it gets completed, is going to go, oh, this BDEV IO just completed. I need to call PT complete IO, because that's what I provided when I submitted that IO. So you can see the other thing I mentioned, that last parameter that I called was the callback argument. The first thing that we do here is we cast that callback argument to something called the original IO, right? Because it's the original IO. This completion is for the IO that I created in the vBDEV pass-through module. So now I know that this BDEV IO that's called the completion. This is the one I created. And the callback argument is the one that was originally sent. So now I'm going to do whatever I'm going to do with the completion, if I'm going to do anything with it at all. And I'm going to complete the original I/O, right, with whatever status either came back to me or is a result of an operation I did, either on my submission or completion end. I'm going to complete that I/O back up the stack, and then I'm going to free the bdev I/O that just completed, which is the one that I allocated because I'm a vbdev pass-through module itself. So again, conceptually, we're intercepting I/O, but implementation-wise, we're actually, oh, okay, I get this I/O. I'm going to send a new one to the target, and when that one comes back, I'm going to complete it back, and I'm going to free the one that I allocated when I did my operation. One other kind of cool thing to note on this slide, this is just sort of a silly example of a capability in the block device abstraction layer that is, you can think of it as kind of like an extension to the I/O. So when we initialize this function, and you didn't see that in the code, but you'll see it in the lab tomorrow, and you'll certainly see it if you go look at the code. When we initialize the bdev in this module, we tell it the size of any per I/O context that we want to save as a module for these bdevs. So I can put anything I want there. You know, I give it the size of a structure and my own structure, and the block device abstraction layer will carry that pointer along with this I/O through its life cycle. So if you remember, if you were looking closely at the submission slide, I just took that context pointer and just said, all right, I'm going to put a 5A in here just for the fun of it. So now in the completion, I'm just testing here to say, hey, look, is this context that I passed along with the original I/O, is it still what I said it was? So obviously this isn't, you know, a useful example other than being an example, but this is how you store your own per I/O context and get it back on the completion side. Okay, so again, a lot more about this in the lab tomorrow, specifically about virtual bdevs and using the pass-through module to go through some exercises. Again, this is mostly around calling attention to the fact that virtual bdevs are extremely cool. There's a bunch of examples, including one that just does pass-through. And we want to make sure everybody knows that and really uses it and recognizes the value in this capability. So, any questions before alcohol? No? Okay, good. Oh.
Is this virtual bdev actually encapsulates or abstracts multiple physical bdevs behind it? Is that correct, or is that a one-to-one mapping?
You know, it's, I think this is the back button. Let me see. I've got a picture that shows it's definitely does, it can be pretty much anything you want. So here's a picture that sort of shows a little bit. You can stack vbdevs on top of each other, on top of one bdev. So there's a one-to-one mapping, and you can create an I/O pipeline with different things doing different things. So I could have a compression vbdev, a crypto vbdev, and a single vbdev bdev. It's a good thing we're doing this before the alcohol. Underneath. Over here, what I'm showing is a single vbdev representing two underlying bdevs. As Jim mentioned in one of his talks earlier, there's actually two different implementations of this concept out for review right now. So this is basically spanning or pooling or aggregation, RAID 0, whatever you want to call it. We're taking two things and turning it into one. There's also another patch floating around out there that does RAID 1, which would take both of these and create one vbdev out of them. So it's definitely not a one-to-one. It's extremely flexible.
So an I/O submitted to vbdev, it gets split across multiple bdevs, so it waits for the completion across all of them. So that all that thing is covered as part of vbdev I/O completion. Rather, when an I/O is submitted to vbdev, does it send it to multiple bdevs?
Yeah, that would be the responsibility of the vbdev module to keep track of that. Okay. And again, all three examples that are out there right now, the RAID 1 and the two around pooling, all show how you sort of spawn child IOs and keep track of them associated with the original IO and make sure you don't complete the original IO until you understand the status of all the completions of the children IO. All that's going to be in the vbdev module that implements that capability.
Okay. Thanks.
So before we get to the next question, when we ask the next question, that gives you a little bit of time to fill out your survey and get 10 more tickets in. So if you haven't done it, I'm stalling just for a moment because I want to give you guys just a little more time. So with that, go ahead, ask your question. Get them in.
So
Oh, yep, sorry. I'll clarify. These are Intel Optane SSDs that you'll have a chance to win. So,
Is your mic on? I'm not sure. Is the mic on?
I think so.
Oh, there you go, yeah.
So consider a very simple application where the BDEVs at the bottom here are NVMe devices,
Yep.
and you're just simply aggregating their capacity.
Right.
If they're NVMe OF devices, do you have to stay within a node? Do you have to stay within the green box?
You don't. Whatever's down here can be pretty much anything. And I think it was Jim's deck, or if not, somebody's deck today or yesterday, we could find it, showed example of where that back end is actually the NVMe OF initiator. So you're actually going off node for your storage. So you could do this, and these guys don't have to be in the same box. Obviously, you're going to have a whole lot of other conditions to deal with if you do that, but the architecture supports it for sure. No, it's a good question. Thanks.
oh, over here we got.
So eventually, will we have like this extended to the blob store level as well? Like have multiple, create a single blob per SSD, and have multiple blobs together shown as a single blob at the VBDEV level.
That's basically logical volumes.
Okay, so that feature will be.
It's there.
Is there?
Yep, and Daniel's talk tomorrow. We'll go into a good amount of detail on that, and obviously everybody's here.
Okay.
But yeah, that's what it does.
All right, thanks.
Yeah, you bet.
Okay, so one more question here.
Sure.
So for managing those bdeVs, is it the idea like we have a multiplexer at the bottom layer, and then we tag the traffic from different bdeVs, and then after we have a single completion thread listening to check the doorbell, and then we, according to the tag, distribute them to different processes? Okay.
It might be easier if we turn the mics off. I'm like hearing double, or maybe I'm too close, or I should stand next to that. Okay, try that one more time.
Yeah, I'm thinking, so the virtual bdeVs, so
Right.
the users of virtual bdeVs, are they separate non-cooperative processes, or they are somehow cooperative?
So the virtual BDEVs themselves are independent abstractions that you send I/O to. What ties things together is how you build the configuration and who your application is talking to, right? So in the case of, like this picture where I've got these things stacked, the only reason they're stacked that way is because the assumption is there's a configuration file that said this VBDEV is going to claim this BDEV, and this VBDEV is going to claim this type of VBDEV.
Yes,
so
so-
that's what creates the association. Other than that, they're completely independent.
So can they share the same IOQ pairs? If they share the same IOQ pair, then I assume they're mixed together in some
Yeah,
way.
and now we're starting to talk about getting into some problematic areas. Yeah, maybe we should have that discussion after we grab a beer. And
Yeah, sure.
Ben and Daniel are here too, so they'll
Thank
love
you.
to talk about that. All right, thanks. Any other questions? All right, everybody's already at the bar. Awesome.
All right,
Thanks.
so thanks, Paul. Good stuff. Appreciate it. All right, so we're going to do some drawings.